Okay, so I want to take a look now at some sum formulas. This is going to tell us what the sum is actually equal to. That's different from the rules, which is how I can manipulate it to write it a different way. This is going to actually give me a formula for calculating what a sum is equal to. And so for these formulas will be true if the initial index is 1. Okay. So let's start with letting c be a constant. And let's suppose that I'm adding up the sum as I goes from 1 to n of c. So I'm going to think, okay, my index starts at 1. And I'm just going to keep counting until I hit my final index, or my upper limit of summation, which is n. Now, when my index is 1, my term is c. When my index is 2, my term is c. So for every value of the index, I'm getting another term of c. So I'm just getting a whole bunch of copies of c. c plus c plus c plus c plus c. How many times? I'm getting n copies of c. But I know what that is. That's just n times c. So if I'm adding up a constant, I get that constant however many times I have number of terms. And if I start at 1 and I go to n, n is the number of terms that I have. So I'm getting n copies of c. Now this is one of those formulas on the formula sheet that has a little asterisk by it. That means I expect you to know this one. Okay. Basically my rule is this. If I can give you an explanation for why it's the correct formula so that you can understand it without having to just memorize the symbols, then I'm going to expect you to know it. Okay. But if there's not an obvious sort of intuitive explanation of why that's the right formula, then I'm not asking you to memorize it. Then I would give it to you if you needed it on an exam. But this one definitely makes sense. Now, if I did start with a value, well, let's just take a look at two quick examples. Okay. So if I had the sum as I goes from 1 to 500 of 3, that would be 3 times 500. So it's 1500. I'm just getting 500 copies of 3. 3 plus 3 plus 3 plus 3. Repeated addition is just multiplication. Okay. Now, if I had the sum as I goes from 2 to 500 of 3, that is not 1500 because I don't have 500 terms, because I didn't start at 1. Okay. Here, this would be, here's sort of the way I think about it. It's the sum as I goes from 1 to 500 of 3 minus 3. That would be the term when I is equal to 1. So now I can say, oh, that's 500 copies of 3, so this would be 1500 minus 3. It would be 1497. So all of the formulas that we're going to be going over right now assume that the initial index is 1 to give us the correct answer. If we start someplace else, we can adjust the formulas to say, hey, we left off some terms, so let's subtract them from what the sum would be. Okay. All right. Now, the next sum I want to take a look at is the sum as I goes from 1 to n of I. So just adding up the first n positive integers. So notice this is just 1 plus 2 plus 3 plus 4 plus all the way until we hit n. Okay, so it's just adding up the first n positive integers. What I'm going to do is I'm going to start with an example to sort of explain the thought process, and then we'll see if we can generalize that to get the formula. Okay. So if I were doing the sum as I goes from 1 to 100 of I know that that would be 1 plus 2 plus 3 plus 4 plus 96 plus 97 plus 98 plus 99 plus 100. And of course, I would have all of these terms filled in. Now, here's the not very efficient way of adding all of these up. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus, oh, I forgot where I was. Okay. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7, oh, I lost where I was. Let me start again. Okay, so if you see this, you're tempted to just add them up in order. But there's a much better way of adding them up. I'm going to take this first number and this last number, and I'm going to say, hey, that gives me 101. Whoops, that gives me 101. And then I'm going to work my way in. So I started with the smallest number. I'm going to start with this, then go to the second smallest number and the second biggest number. 2 plus 99, oh, that's 101. 3 plus 98, that's 101. Because every time what I'm doing is I'm making my first number 1 bigger, but I'm making my second number 1 smaller. And so those changes cancel out, and I'm always getting a sum of 101. So I'm going to just be getting a bunch of copies of 101. How many copies? Well, if there were 100 numbers on the list, and each pair gives me 101, I've got 100 numbers, I've got 50 pairs. So this is going to be 101 times 50, which is going to be 50,500. No. I can do basic arithmetic. It's going to be 5,050, sorry. Zeros. Ugh. Okay, it's going to be 5,050. It's 50 copies of 101. Okay. And I can do that anytime I'm adding up consecutive integers. So, if I'm going from 1 to n, I'm going to say if I pair them up, working from the outsides in, the smallest plus the biggest is going to be n plus 1. That's the sum I'm going to get from each pair. So that's the sum of a pair. And then how many pairs do I have? Well, if there were n numbers, there are going to be half as many pairs. So n over 2 is the number of pairs that I have that add to that. Now, in this example that we did, we had an even number. So we got an even number of pairs as well. If I have an odd number of terms, does this still work? And the answer is yes. Let's just take a look at the sum as I goes from 1 to 7 of I. So that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Odd number of terms. Okay. But 1 plus 7 is 8. 2 plus 6 is 8. 3 plus 5 is 8. This one extra term, that's like half of a pair. And notice it's giving me half of an 8. So I could say this is 7 plus 1, the biggest number plus the smallest number, times 7 halves. That's 3½ pairs. Each pair gives me an 8. The half pair actually is just a 4. So this would be 8 times 7 halves, which is going to be 28. Okay. So it works even if n is odd, but it's just the sum of a pair times the number of pairs. Now, you'll often see that simplified and written as a single fraction, n times n plus 1 over 2, or even n squared plus n over 2. Any of these versions are fine, but as far as remembering it, this is how I think about it. That's the sum of each pair, that's the number of pairs. So, this formula is also one that is starred on the formula sheet that you can get on the class website. This one I do expect you to know. I won't give it to you if you need it on exams. Okay? And that's because we can understand why it works. Now, it turns out there are two other formulas that we're going to be using a good bit. There's the sum as I goes from 1 to n of I squared. Okay. And that is n times n plus 1 times 2n plus 1 all over 6. Why is that true? I don't really have a good answer. I don't have a simple explanation for why that's true. Now, for those of you who are in the honors section, we can prove that it's true using a proofwriting technique called induction. And so that's going to be the last honors worksheet that the honors students complete, is on proofs by induction, where you're going to be proving a couple of these sum formulas. This here wasn't actually a formal proof. I could formally prove this by induction. This was an informal explanation, but that helps me to remember it. I like informal explanations. Proofs by induction are kind of cool. I think they're fun to do, but it's rare that they help me remember what the result is. Okay? Whereas an informal explanation can help me just to remember what the result is. Okay? So this is one that if you need it on an exam, I would give it to you. Okay? So you don't need to have this memorized. And then the last one is the sum as I goes from 1 to n of I cubed, and that's n times n plus 1 over 2 squared. It's kind of interesting. It's this formula squared. So basically, we've got formulas so that we can add up 4 types of things. We can add up constants, we can add up consecutive integers, just I, squares of integers, and cubes of integers. Okay. So what we're going to do in the next video is just practice a little bit using some of these formulas in conjunction with the rules of sums, and then we're going to apply that to Riemann sums. So we'll set up a Riemann sum and take the limit of a Riemann sum in order to actually evaluate a definite integral.